remain, and I start the condivision of the PowerPoint presentation. You'll tell me whether you can see. Do you already see the PowerPoint presentation? Andrea, con cui parlavo prima, mi ha sentito? Si vede la schermata di PowerPoint?
Si è visto un attimo, poi adesso è diventato tutto nero.
Oh, yeah.
Adesso si vede.
Ah, adesso si vede, bene. Okay. So now let's see where we were. A little bit lower. Okay, we were talking yesterday about Eudoxos of Cnidios, and we will resume our discussion from there. You see it full screen?
Yes.
Okay, great. There is an interesting point in Republic, in Plato's Republic, where Plato was sort of polemizing very softly, to be honest, with those who were trying to make, so to say, by quote unquote, mathematical models of the motion of the stars, of planets and stars, saying that in nature nothing is perfect, because his philosophy of ideas was developing strong already. It was at a very good stage of development. The basic idea in Plato's theory was that what we see as material reality is just a copy of the ideas, the pure ideas, conceptual ideas that in that world, that is the world of ideas. We will later discuss that point more extensively. And so he was polemizing with those, he doesn't mention names, with those who expect the motion of the stars to be so precise as to admit a sort of geometrical, as he was saying, description. It is clear that that was a sort of address for, I mean, he was addressing with this sort of criticism his own student, pupil, Eudoxos of Cnidius. But later, in his later maturity and when he was already old, Plato's reconsidered this sort of statement he had done, and was trying to give himself an explanation why these models, and again he was implicitly referring to the models of Eudoxus, were so precise. How could it be that the stars and the planets move so well and in such a, as he expressed himself, punctual way, differently from what we observe in the earthly experience of reality. And his answer was that probably because the stars and the planets have a non-material, purely material nature, but they are perfect like divinities. And we should also be very much careful about the interpretation of God status, divinity status in Plato's philosophy. We should not automatically think in the terms of religion. It was quite different way of understanding the meaning of the world, of the word, sorry, that became clear in his latest dialogues, the last and most profound series of few dialogues to which Timaeus belongs. The Republic is probably the most famous of Plato's dialogues, but it was written at an earlier stage in Plato's maturity. So there was a further development of Plato's philosophy later on, and so he reconsidered it. But of course he had to reconsider, because these models were amazingly precise. So now I have one of the, I'm now referring to our Chinese girlfriend, Leah, and I hope she can read a little bit the Italian as to understand the text I am presenting here, but I'm also describing it in English, so I think she will be able to follow. Did you hear me, Leah? Leah, I don't know whether I'm trying to.
Yes, I can hear you.
Okay, and I will be grateful if you tell me how precisely should I pronounce your first name or second name. It is not clear to me what is the first and what is the second name.
Liang.
Liang.
Yes.
Okay. So, as we were saying, Eudoxos of Cnidius, was, according to tradition and to witnesses that we have, traces of his life that we have in other writers, was born around 408 in Cnido, in fact. And we have only some scattered fragments of his works, of his scientific papers, but we can reconstruct with a certain degree of sureness what he did, because we have information, in particular from Aristotle, in some points, and the most important source of information is the anonymous author of the scholium, as it was called, namely the commentary to the fifth book of Euclid of later times, probably written by Proclus. I already stressed that the fifth book of Euclid's Elements is reputed to be based mainly on the contribution of Eudoxus. So the time when Eudoxus was in Athens and followed Plato's lectures in the academy is probably to be considered around 385 before Christ. But before, very, very young, as you can imagine, looking at the birth date, when he was very, very young, and before meeting with Plato, he had made a trip in so-called Magna Graecia, which means southern Italy, as you know, in the Greek cities. And the most relevant stop he made in these trips to Magna Graecia, was the stop in Taranto, in Taras, as it is in English, where he had a very proficient, a very important for both of them interaction with Archytas. After the stay in Athens, he came back to Cnido, and another thing that we know is that in the years from 381 and 380, he was in Egypt. This was a very important thing, because it is clear that he was interacting with the priests in the so-called temple of Heliopolis, where these priests were also, by quote unquote, scientists, astronomers. They made very many observations. Egypt, of course, is a good place for astronomical observation because it's a desert-like country with clear nights, with no much humidity, almost no humidity, so the visibility of the stars is excellent. And these priests, Egyptian priests in the Heliopolis temple had something similar to astronomical observatory. They conducted many observations. At the time, all observations were made with the naked eye. There were no telescopes, as all of you know, but nevertheless, people were able to keep track of the motion of the planets. So Eudoxus was able to become aware of the registration of the motions of the planets. He made observations himself. That was a very, very important fact. Very much similar to what happened in modern times at the beginning of the Renaissance, when Copernicus and later Kepler were able to take advantage of the extraordinary amount of data collected also with the naked eye by the Danish astronomer Tycho Brahe, whose observatory is still standing in the middle of Copenhagen. It is a tower and that dates the end of the 15th century, and it still stands there. And on top of that tower, Tycho Brahe, for many, many years, conducted a lot of observation and had an incredible amount of data that were very carefully registered. So Eudoxus, almost 2000 years before, made the same thing with his trip in Egypt, to Egypt. And it was then his real imaginative and amazing construction to make a reproduction of the data, of the motion of the stars, and by stars mainly it was meant planets, because the other stars, the real stars, at the time no one had any idea of the distance of the Earth from the stars, but it was clear to many people, almost to all the ancient people, that there were fixed stars, stars that did not move in the sky, and stars that made motions. And the stars that made motions are what we call the planets. And by the way, the word planet comes from the Greek and means exactly those that are vacant, the vacant ones, those that go around in space. Why? The fixed stars stay fixed. Now, the point is that no one had any idea of measuring the distance, was able to measure the distance, but to observe the observable motion, people were able. So the mathematical models of Eudoxus of Cnidius is absolutely astonishing, because he invented a representation of this motion by means of what were called spheres. But there are a lot of indications that actually he was absolutely aware in his own mind that you should not take this idea of the spheres as physical ones. It was essentially thinking of the spheres as a mathematical model. And we will translate this model into modern language, and you will see that it is really very simple to do it. And there is no need of spheres. It's only a composition of rotational modes. But the way it was described is the following. You had a sphere, a principal sphere, that rotates around an axis. Now, this principal sphere that rotates around an axis actually is the representation of the daily rotation of the Earth around its axis. These spheres with a certain radius is such that you fix the endpoints on the rotation sphere, on the sphere that rotates, and that is here depicted as a circle. You fix two opposite points, and you define, therefore, an axis for another sphere that has a rotation angle inclined with respect to the basic action of rotation of the first sphere of a certain angle. Finally, on the second sphere, you fix two opposite points that define another axis of rotation. And this axis of rotation has an inclination of a certain number of degrees with respect to the rotation axis of the second sphere. And you could go on. Now we will see mathematically how you might invent a model with an unlimited number of spheres, whose parameters, therefore, are the inclination angles of each rotation axis with respect to the basic one, the first, and then the inclination with respect to the second one, and so on and so forth, and the rotational speed, the omegas. Now, we will focus on one of the simplest of Eudoxus' models. He made a model for all the planets that were known at the time, that are 5. And every time he succeeded in obtaining a very good phenomenological, we would say, model of the actual motion that you see, with essentially 3 spheres. Now, we have the following. For the moon, all the spheres are concentric. And they have, therefore, different rotation velocities, different periods, and there are different inclination axes. Now, all this was explained in a book that would be extremely interesting if we could read it, but unfortunately it is lost, as most of the books of ancient science. It was called Peritakon, namely about velocities. But we know it sufficiently well, the model, because in Aristotle's Metaphysica, there was a summary, an explanation, and even a larger explanation was provided by Simplicius, the same Simplicius that appears in the dialogues of Galileo Galilei many centuries later. Simplicius also was an Aristotelic philosopher and made a comment to Aristotle's works, and this commentary that contains a summary of Eudoxus' construction is named De Cielo in Latin, De Caelo with the restituta pronunciation. Okay, so the first angular velocity in the description of the moon is 2 pi over 24. This 24 is clearly the number of hours in the day. So it is describing the daily rotation of the Earth. Next, we have an axis that has an inclination of 203.2 grade with respect to the first. What is this angle? But this angle is something that modern astronomer interpret very easily. It is just the inclination of the moon orbit with respect to the plane of the ecliptic. Namely, it is the inclination of the rotation of the moon around the Earth, the plane in which the moon moves around the Earth, with respect to the plane on which the Earth moves around the Sun. And this plane is called the ecliptic plane. So the inclination of the angle is precisely, no, sorry, I told you a complete idiocy. This is the inclination of the Earth axis of rotation with respect to the plane of the ecliptic. It is that inclination that makes the Sun, go up and down during the day in the sky. So this is already interesting. Eudoxus had enough astronomical knowledge to understand this axis, which now we interpret from an heliocentrical viewpoint, but it remains the same angle, even if your system of reference is reverted, is the inclination of the orbit of the Sun with respect to the orbit of the moon. Now, in Eudoxus' model, the second sphere is extremely interesting. It is something that is related to the so-called nutation. So that means that the ancient and the Egyptians, probably also the Babylonians, had already observed what nowadays we know perfectly well, is the period of 2,772 years that takes the axis of the rotation axis of the Earth to change position and with respect to the ecliptic. So you know that we have seasons just because the rotation axis of the Earth is not perpendicular to the ecliptic plane. But the rotation axis of the Earth makes a rotation around the vertical direction. And the period of this rotation is 25,772 years, which is a very long time. And after that, we have an interchange of the seasons. Nowadays, we are in summer when we are closer in the northern hemisphere. We are in summer when we are closer to the aphastron, to the aphelion, namely when we are closer to the sun. And we have winter when we are in the opposite point, namely to the perihelion, and we are in summer when we are close to perihelion, and we are in winter when we are close to the aphelion. But after 25,772 years, it will be the opposite. We will be in winter in the northern hemisphere, close to the perihelion, and we will be in summer close to the aphelion, and vice versa for the southern hemisphere, because the axis of rotation of the Earth will have completely changed direction. Now, this inclination and this rotation is another motion that is called the nutation. And this nutation has a period of 18,6 years. So there is an apparent oscillation of the axis of rotation due to the fact that actually the axis of rotation is going around this path that takes 25,000 and etc. years. So we have this apparent oscillation that is just the projection on the ecliptic of this rotation, and the period is about it is a smaller motion, right? It is about 18,6 years, namely 6,798 years days. This in the apparent motion that we see from the Earth, that is called, this nutation is the revealed as what is called the regression in the nodes of the moon. What are the nodes of the moon that can be ascendant or descendant? They are the points where the moon crosses the plane of the ecliptic. In its motion, the moon that is not aligned with the ecliptic but has an angle goes sometimes upper in the zodiac, sometimes down, and it crosses the plane of the ecliptics at a certain point, and that point is called a regression point. But these regression points in the sky go around during the time, just because of the notation I was referring before. And so, thanks to the data observed by the priest of Heliopolis, Eudoxus was able to incorporate this motion in his model, and he arrived to the period of 2 pi divided by 24, that is the year, 27.2, and times 223. And 223 means what? Each of these numbers has a precise meaning. It has the 24 is the number of hours in a day. 27.2 is the actual period of rotation of the lunar month. Lunar month is approximately 28 days, but only approximately. Actually, it's 27.2 with some approximation. That was at least the approximation of Eudoxus. And 223 is the number of lunations, namely the number of lunar years. The number of complete rotations of moon around the Earth. So it came with this frequency, and he assigned the rotation of with this inclination of about 5 degrees from the North Pole to the second sphere, giving this specific number, this specific velocity that accounts for the notation in modern language. Finally, he introduced omega-3, and that omega-3 is the most clear of all the periods, because it is just the rotation time of the moon around the Earth. 24 hours in a day, 27.2 days. But omega-3 is the rotation of an axis that has an inclination of this famous angle, very small angle, not so small angle, 23 degrees and 27 seconds of arc, and that is the angle, as we were saying, of the rotation axis of the Earth with respect to the plane of the ecliptic. So 5 degrees is the inclination of the plane on which the moon rotates with respect to the axis of rotation of the Earth. And 23.27 arc of seconds is the inclination of the axis of rotation of the Earth with respect to the plane of the ecliptic. And there are these three periods that are explained. The first is clearly explained, is the day. The lunar month is 28 days. That is also clearly explained. But the most subtle of all is this period of 223 lunar months. That is a very minor phenomenon that, however, from historical data, Eudoxus was able to work out. Now, let's see how we can implement in modern language this model. It is very simple. We just have to introduce rotation elements. A rotation is an element of the SO3 group. And there is a very simple formula. If you want to describe in three-dimensional space the rotation of an angle theta around an axis, unitary axis, that has coordinates LMN. So LMN are the Euclidean coordinates of an axis in 3 dimensions. The sum of the square is equal to 1 because we take just a unit vector, so in that direction. If we want to describe a rotation around this axis, we just have to introduce the generator, which is an antisymmetric matrix that has the component LMN of the vector disposed in the way I have shown. So this is an antisymmetric matrix. It is an element of the SO3 Lie algebra. And if you multiply by theta this matrix A, and you take the exponential, then the exponential can be easily rewritten in this way. It is the identity matrix plus the original matrix, the generator, multiplied by sine theta, plus 1 minus cosine theta for the square of the element. So that is the way we usually write a rotation around the axis. Particularly if we take, for instance, the rotation in the xy plane orthogonal to the vertical plane, we obtain the omega 1, which is the typical rotation matrix in a plane. But if you want to describe the rotation around an axis that is not vertical to the xy plane, you have this general and variable formula. So now what you do? Now you simply compose what the Eudoxus model means is that you have a first sphere that rotates, and you apply the rotation matrix. So what you say is that the angle is proportional to time with the angular velocity you gave. You put theta equal omega 1 for your angle. So omega 1, O1, is the original rotation, reference rotation, and it is the rotation of the Earth around its axis. We have taken the Earth rotation axis as the reference z-axis, and therefore we have an xy plane, and that will be what it is. Secondly, we say that we have another vector, a vector that is inclined of an angle θ2 with respect to the axis of the Earth. And this angle is, as we said, 203.2 degrees. So you convert this easily in radians by multiplying by 2 pi over 360, and you can write, therefore, the following formula for the instantaneous rotation axis of the second rotation, because we fix this axis of rotation to the sphere that rotates around the first axis. So this vector that at time 0 is just inclined in this way, sin θ2 0 cos θ2, at a later time will be the result of applying the rotation matrix with this associated with the vector v1, so the first that we have defined. We will apply it to the v2 vector, and we will obtain the v2 vector at 0 time. We will obtain the v2 vector at time t. At this point, it is very easy to do the next point, the next step. Namely, we create the rotation matrix with angular velocity omega 2 of t around the axis v2 at time t. So you see now we compose the rotations in this way. And I think is now obvious. You could make as many steps like this as you wish. At each time you introduce a vector with a certain angle with respect to the previous one, you introduce a new angular velocity, and you do the subsequent rotation matrix. So we have the rotation matrix Vj plus 1 is given by the rotation matrix omega jt on the vector omega j plus 1, and omega j plus 1 of t is just the rotation with frequency omega j of t around the axis vj plus 1. It is just a iterative construction. And at this point, you can just take any vector and apply the final composed rotation as a function of time. You take a fixed vector and you write the vector x t, y t, z t that follows from that. Obviously, what you obtain is a curve in space. These are the coordinates in three-dimensional space. And the result is depicted in this picture, something that you can construct yourself with a little programming computer, but very simple one. And you see the periodic motion in green, yellow, and x of the three coordinates. The three coordinates, vertical and in the plane, vary, but with periodic motion with a lot of oscillation. And now the final result is that you can project the actual motion of the moon as seen in the reference system of the Earth. And in addition, we have depicted the ecliptic plane, which in the reference system of the moon is seen as obliquous with respect to Earth. It is the opposite. We are actually, it's our Earth that is going around the sun, as we know, but it's just a matter of reference point. So you have a curve that is quite complicated, as you see, and this perfectly matches with, even in modern times, the actual motion of the moon as it is seen from the Earth over not just 1 year, but over the centuries. And that was possible thanks to the astronomical observations of the Egyptian priests. So you see, this is extremely interesting. The sophistication of Eudoxus' description of what is the motion of planets. For him, the moon was just a planet. It was just one of the celestial bodies that are going around the Earth. But he had data. He himself verified data. But such a thing that as a period, I mean, there is inside a period that is about 19 years, could not be verified, could not even be thought of if there were not registers of historical data. And that tells a lot about the long history of astronomical observations of the Egyptians and the Chaldeans, as the Babylonians were called in ancient times by the Greeks. So there was a massive amount of data that were refined and taking a completely Earth viewpoint, as it was natural at the time. Greek mathematician of the beginning of the first half of the 4th century was able to construct such a sophisticated model that is still valid for your observation if you have the precision of a domestic telescope. Of course, there are more effects if you have more precise instruments, but it's spectacular when you think that all observations were made by naked eye. The astronomy of the Greeks of that time was by no means primitive. It was really very much sophisticated. And also mathematically, it was very much sophisticated. But there was a prejudice. The prejudice, which actually turns out in the first attempt, without knowing, of what nowadays we call Fourier analysis, of decomposing a periodic curve into harmonics. The only thing that the Greeks were able to think of were constant velocity rotations. The sphere was the only model they were able to conceive, because it was perfection. The sphere was what we can call the most perfect object, because it's completely symmetrical. And from their viewpoint, the only possible motions are the straight motion with constant velocity, or the constant rotations with constant angular velocity. But the genius of this geometers and experimental, at least observational astronomers, was that they had data, they were taking seriously the data, and they were trying to explain the data in a mathematical way. And they reached the perfection of such models. 400 years later, in the surviving work of Claudius Ptolemaeus, the Almagesto, we will talk a lot about that. These models were even more developed, and Ptolemaeus introduced the cycles and epicycles, but the essence of the idea is there. And we should not discard this as saying, oh, but they were in the they were not considering the right viewpoint, namely that the Earth goes around the sun and not vice versa. This is just a matter of reference system. It is not really so important. It was important to change viewpoint in order for Newton's and Galileo later, Galileo and Kepler and then Newton, to explain in the new Copernican system these simpler orbits with the physical law, Newton's law. But in fact, as later general relativity has shown us, you can use whatever reference system you like, because physics is the same in all reference systems. So we should not historically, it is very important, the Copernican revolution, because it simplified the picture of the orbits and drew Newton to conceive the principle of general gravitational attraction and the Newton's law, which, however, as we know, is not the end of the story, because later it was superseded by general relativity that erases the notion of potential and thinks in a different way. But the advancement of the Greek mathematician, in particular of Eudoxus, is incredible. Now, as I told you, the other scientist that is extremely important to consider is slightly older, and who was, as I already told you, was close friend of Plato's and even saved him from Dionysus in Syracuse, is Archytas. Archytas is not famous for astronomy. At least we don't know of contribution of Archytas to astronomy, but he was a prime rank geometer. And now we will consider one of his most spectacular contribution, which also we know this contribution again, not from the original paper that's lost, but from the report that was done once again, usually through commentaries of centuries later. Not too late. And we have also, differently from the case of Eudoxus, a picture of his head in this sculpture, which is conserved in Naples. I already told you that Archytas was friend of Plato, and he was also a politician. He was for a long time, it seems for 7-8 times, the strategos, namely the leader, the head of the state. It was a yearly charge of Taras, and Taras was the most important city on mainland Magna Graecia, and I also told you that Taras was founded by the Spartans. It is the only colony due to the Spartans. All the others were of other cities. So, differently from Athens, the version of Greek that was spoken in Taras was the Doric dialect. And the same is true of Syracuse, who was instead founded by the Corinthians, who were also from Peloponnesus, and therefore they also spoke Doric dialect. Classical Greek literature we mostly know of was in the Ionian dialect of Attic. It was in Attico, in the Attic dialect, which is well, close to the other dialects, but substantially different in many respects. The Greeks could understand each other very well, but I mean, we should have a model to to understand what was the situation in classical Greek at that time, thinking of the Italian dialects. I mean, like Genoese dialect with respect to Piedmontese, or even with respect to Southern dialects. That was the span. In classical Greek literature, the one of the authors that expressed himself more in Doric than in Ionic was Pindarus, the great poet Pindarus. But almost all the body of Greek literature, the tragedies, the poems, the first historians, Herodotus and Thucydides, they express themselves in Ionian, Attic dialect and Ionian dialect. They're very close. So the dialect spoken by Archita was certainly Doric. So his papers were written in Doric. And the same is true of the original papers of Archimedes. We have papers and books of Archimedes surviving, but they were written in Doric. And what we have nowadays is not the really original Doric version. It was the conversion from Doric into in what was called later the Koine dialectos. At the Hellenistic times, with after the adventure of Alexander the Great, who founded the Hellenistic Empire, expanded the Greek civilization into the East, making a contaminatio, making a compromise, because it was not one way, it was two ways process. The Greeks took a lot from Babylonians and Egyptians and vice versa. And of course, the world became much wider. And there, at that time, developed a new type of Greek that was called Koine dialectos, namely the common dialect. It was a compromise among the various dialects, and it was the Greek that was spoken later in Egypt, in Syria, and almost everywhere in the Roman times, in the eastern part of the empire. And it is from the Koine dialectos that came later the medieval Greek language of the Byzantine Empire that slowly transformed with a lot of additions into modern Greek. So it was in Roman times that Theon of Alexandria, who was also responsible for edition of Euclid's book, made editions of Archimedes' papers in Koine dialectos. And these are the versions that have survived. So the real original of Archimedes, we don't know. But we are already lucky to have the Greek source in Koine dialectos. As far as Archytas, whatever he wrote was certainly in Doric, but nothing remains. But we have the usual indirect sources for him through other authors, including Archimedes. So there was the Greeks had a completely geometrical picture of, I mean, they privileged geometry. They were thinking geometrically, not yet analytically. Arithmetic was considered very important. And it was even ancient, because the development of our arithmetic dates back to Pythagoras. But there was the crisis in the Pythagorean thought, because the Pythagoreans' philosophical school that developed also in Magna Graecia, in Croton in particular, in present Calabria, and earlier, because it was in the 6th century. They had understood many important things. For instance, understood the principle of musical harmony. They understood that the good sounds come from harmony, namely the fact that you make superposition of frequencies that are in simple ratios, 4/3 and so on. So the rational ratio of the frequencies, we would say modern language, is what makes harmony. So they were giving a lot of emphasis to the fact that the numbers are very important, and the ratios are rational numbers are very important, rational integers, and made a philosophy where numbers were considered the essence of things. They tried to make a metaphysics based on numbers. But then there came the crisis when the geometers, even of their own school, because it was a large school, and Pythagorean group was a sort of monastic club. They used to live together, the followers of Pythagoras, and divide expenses and live together, sort of like monarchs. They were scientists, they were researchers, but this sort of spiritual approach to life, where they devoted themselves to arithmetic and to this philosophical vision of nature as based on numbers. But inside the schools himself came the realization that you have incommensurable things like square root of 2. I mean, the area of I mean, Pythagoras' theorem itself, if the sides, the catetes, are not in special combinations, so that the sum of their square is another perfect square, is not an integer number expressed by integer numbers. So they discovered the rational numbers. And the legend goes to the point that the Pythagorean scholar who discovered the rational numbers drowned himself in the waters of the Mediterranean for the shame that he proved in having discovered such a nasty thing like irrational numbers. Others were wiser, and it is a legend, it's not sure, tried to make, I mean, to come to terms with this matter of fact, and so started just a sort of rush to classify irrational numbers, to demonstrate that the square roots of certain numbers are irrational. Namely, you cannot construct them as rational numbers. It was not obvious, and there was a moment right in Plato's time when someone was convinced that there was a finite number of these irrational numbers, and it was XXth. I already mentioned XXth of Megara. He was an Athenian who died in a battle at the end, and is mentioned in one of Plato's papers. He was one who, continuing the work of Theodorus of Cyrene, Cyrenaic. Cyrene is a city on the northern coast of Africa, present Libya. You certainly know that. Theodorus had started this inquiry about irrationals, and it is reported that he had proven that square root of 3, square root of 5, square root of 7, square root of 11, 13, 15, up to 17 are all irrational. Namely, you cannot represent them with rational numbers. But they were proving geometrically, with ingenious constructions, this statement one by one. It was Theaetetus, who had been younger than Theodorus, who was the first to construct infinite series of irrational numbers, showing that there are infinitely many of them. And that is reported in the dialogue, Plato's dialogue, entitled Theaetetus, where Theodorus and Euclid of Megara and Socrates appear as characters. So why I'm saying this? Because now you will see something spectacular. There was one problem that was exciting the fantasy of Greek mathematicians for several decades, and many tried to solve it, that in modern language is a triviality. Suppose you have whose side is longer A. A what? Well, they were thinking in foot or in length of an arm. But let's say foot was like it remained in England at distance. So let's say that you have a cube that is 1 feet or whatever of side. Then its volume is obviously a cube. Now the question was posed: what is the side of another cube whose volume is twice as much as the volume of the first. Well, if way of today writes a very simple equation. B cube must be equal to 2a cube, which means that B is the cubic root of 2 times a cube, which means that it is the ratio between side A and the side B is simply cubic root of 2. But as I told you, irrational numbers were not something that Greeks did accept as number yet. For them, numbers were just rational numbers at most. And there was all this rush to understand the incommensurability. Each problem was a problem by itself. With square roots, cubic roots were even more difficult. It is a concept that came with time. So it was posed as a problem. And now you will see the sort of ingenious geometry that Archita developed in order to construct geometrically the cubic root of 2. It is almost amazing that in order to find such a simple thing, simple from our viewpoint, Archita developed things that are close to what we will call nowadays algebraic geometry, much more difficult subject. So let's see what was the construction of Archita. And in order to come to that, we have to make this observation, because what we have written here is just an equation. And as I was telling you, and this is a cubic equation. What I saw an algebraic equation. But in the whole span of Greek mathematics for all these centuries, marvelous things were done in geometry. But the very concept of an equation was not yet developed, and was not developed until in the end of the Roman Empire. There were the first steps in this direction by Diophantus. We will talk about Diophantus. But the real development of the idea of what is an equation, and therefore what is algebra, is due to the Middle Ages, and it was developed by what we like to call Arabian mathematicians. Actually, these Arabian mathematicians, most of the time, were not of Arabic origin, but were Persians or Christians, Syrians, and other ethnic groups, although they express themselves in Arabic. So we have to stop for a moment about the concept of equation. Linear equations, in some sense, is a discovery very old. The first equation, linear equation, can be dated back to 1650 before Christ, approximately, and it is contained in a papyrus conserved at the British Museum of London, where, if you read the hieroglyphs, you can see, translating something that was expressed in words that can be expressed with a formula. That is the following equation. You have an unknown that the Egyptians called how. I don't know the exact pronunciation, but I know the meaning. It was called mukyo, the heap, the heap of something. So the heap of something might be subject to an equation. So you could pose problems like the one you see in front of you, that 2/3 of this quantity, of this heap, of this how, plus 1/2 of it, plus 1/7 of it, plus 1 unity of it, is equal to 33, whatever it was, this 33. And of course, any student can easily solve this linear equation nowadays. But it is very, very interesting that the problem of writing something that we can translate immediately into a linear equation was something clear to the Egyptians already about 3,800 years ago, 700 years ago, right? About. And there is another example of that. This is an example that is at the British Museum. There is another papyrus with a similar problem posed and solved, that is instead conserved in Moscow, in the Pushkin Museum. So Egyptians had clear the idea of linear equations, and the Greeks obviously took it from the Egyptians. So in some sense, they were also able to solve such a problems. But the thing is that no one wrote formula like this. This is a translation of something which is described in words. The formal writing of an equation with the concept of unknown, what we usually call X, the unknown, had to wait until the 9th century. And even at that time, essentially, the unknown was clarified by Al-Khwarizmi, but the equation was not written symbolically, but was described in words, which nowadays for us is much more difficult. If you read it instead of writing it formally, it is just something like a problem that you can find the Settimana Enigmistica or something like that. In formula, it's a triviality for us. But the development of abstraction that was implied by arriving at the concept of algebra and of formal writing like this is something that we can think is simple. Is simple by no means. It took a lot of development of thought. And what this appears simple to us, appear very difficult, and they were not thinking in those terms. And instead, they were brilliant people like XXth, because look at what he did in order to calculate the cubic root of 2. Before describing it in detail, let me tell you about the legendary origin of the problem. There are two different historical sources about this. One is Theone of Smyrna, who wrote already in Roman times, so at the end of the 1st century, beginning of the 2nd century, so by the time of Trajan as emperor of the Roman Empire, he wrote in Greek a book which survived, and it is typical of that time that a lot of Greek papers or books had a Latin title, just because it's Roman times, so Latin title, but then a Greek text. And the Latin title was Expositio Rerum Mathematicarum ad Legendum Platonem Utilio, which means a treaty, an exposition of those mathematical items that are useful, I would say even necessary, in order to read Plato's papers and Plato's works. So it was a sort of textbook for these Platonic academies that, as we have already explained in previous lectures, were the analog of modern universities dispersed throughout the empire, the Roman Empire. The various philosophical schools, we already mentioned, there were different ones, but they made a network of schools where the emphasis was on the thought of one important philosopher and later philosopher in that tradition developed their commentary, their explanations, their interpretations of the work of the head of the school, in this case Plato. And so there was a production of a lot of books, I would say textbooks for students, for followers of that type of studies. So Theone of Smyrna was the author of one of them, which, by the way, there is an excellent edition of the original Greek text by Federico in recent 10 years ago, something like that, with an Italian translation and a really interesting critical apparatus of explanation things. It is a really very, very interesting book. I've not read it entirely, but I have gone through, and it is really very interesting. And there is another tradition, which is instead due to Eutychius, who is much later, because he was already at the end of the Roman Empire. In fact, he was born after the traditional collapse date of Western Empire, so he was already Byzantine. born in Palestine. And they both make a reference to Eratosthenes. Eratosthenes, on the other hand, is much earlier. He is a contemporary of Archimedes, and he lived in Alexandria at the times still of the Ptolemaic dynasty, so in the 3rd century before Christ. But although they make reference to the same supposed work of Eratosthenes in with title Platonicus, they refer to the same source, but they tell different stories. According to one of them, there was something that is certainly impossible from the point of view of chronic. Because it was the time of the famous pestilence in Athens and in other cities, and the Delians, the citizens of the island of Delos, sent, as it was usual at the time, a delegacy to interrogate the Delphi's oracle, what they should do. They usually thought that the divinities, the gods, were some kind of irritation because of something that the humans did wrong, and that was the cause of the pestilence. So they wanted to know what they could do. And the answer of the oracle was that the god, in this case Apollos, would forgive them for their sins if they were able to construct an altar for the god that should have twice the volume of the present one. They could not understand how to do it and what was the meaning of such a strange request from the god. And so they sent to Athens another delegation to ask Plato about the meaning. Now, Plato at the time either was not born or was just 1 year old, so it is completely unhistorical. But it is interesting now, nevertheless, because it is a sort of apologus. Plato answered that the meaning of the oracle was that Phoebus, or Apollos, as it was called by the Greeks, was irritated with human race because they were not playing enough impetus, enough they expended not enough energy in the study of geometry. It is clearly a pretextus thing. According to this is the story told by Theons of Smyrna. The story told by Eutychius, which is also attributed by him to Eratosthenes, is more mythological, and apparently, according to that report, Eratosthenes writing to his own king, most probably Ptolemy III Evergitis, would have recalled that when the mythic king of Crete, Minos, the 2000 years before, whose son Glaucus died in his childhood. He was this mythical king Minos was on a rage with the architect that had constructed the tomb for his beloved son, too small, and he had ordered them to make it twice as big. And they made a terrible mistake because they simply constructed another cube. It was more or less cubic shape, with twice as long the side. And so, of course, they multiplied by 8, not by 2, the volume of the tombstone. And everything is legendary, but it is very much interesting to see how the legend put into evidence the complete ignorance still in Roman times, later centuries, of the easiest of all possible problems, using the cubic root of 2. So how was Archita in the beginning of the 4th century before Christ, at more or less at the time when Plato visited him in Taras, solving the problem? He solved the problem geometrically. This is the interesting thing. He conceived the following thing. He introduced, to solve this problem, something that is itself much more important than the solution of this trivial problem. He constructed, as long as we know, the first non-planar curve, closed curve, in the history of geometry. He constructed, by intersection of some surfaces, a curve that cannot be stretched on a plane. In italiano si dice una curva sghemba. And at the basis, I want to stress another point. The way, at the end, I will show you how he constructed this curve and even show you the picture of this curve, which is nowadays still called the Archytas curve. And you can find it in modern algebraic geometry at the beginning, of course, textbooks. But then behind this construction, there was typical concept that was focus center of Greek thought in those times. That was the problem of double average, so-called double average proportion. It is again in modern language a stupid, very simple problem, but it is very, very important to see the relevance that was given to this problem by the Greeks, because this same concept is at the basis of the whole discussion that Plato makes in his Meros, we will see later, and from it he derives a sort of cosmological theory of the world, at the same time discovering the so-called Platonic solids, the regular solids in 3 dimensions. So what is this problem of the double average proportion? Well, it is the following. You have two numbers, U and V, measure that, and here is the very important thing. The very concept of number was not so clear yet to the to Greek philosophers and mathematicians. Because nowadays we have an abstract view of numbers, and that is the reason why we developed. In order to arrive at algebra, you had to have an abstract notion of a field of numbers that now we classify as integers, rational, real, complex, and so on. It is even stated by Aristotle in one of his, I think in the Metaphysics or in his book on logic, I cannot remember. It is often reported that the Greeks, this is something that you learn at school because it is a sort of traditional, popular thing that they tell you. The ancient did not know the zero, number zero. That is an invention of the Arabians. Actually, it's not an invention of the Arabians, it's an invention of the Indians. And it came to the Western world through the Arabians. We will talk about that. But what is not stressed is that even the number 1 was not a number for the Greeks. This is very important. Because Aristotle says that what are numbers? Numbers are what counts unity. The numbers of unities. So 1, that is the unity, is not really a number. And why? Because 1 for us is a number. So it's an abstract concept. For the Greeks, 1 is an extension, is the unit length, the unit square, the unit of area, the unit of something that you count. Let me be precise, say, you count apple. When you say, I have 1 apple, this 1 apple for the Greeks meant nothing. Apple. This is an apple. Then you can have 2 apples. Then you have the number 2 that says that apples are 2. The number 3 that says that apples are 3, and so on. But 1 apple, 1 times apple, doesn't mean anything for the Greek of this centuries, for the Greeks of this century. It was really a conquest of thought to understand unity as a number. So obviously, to say I have 0 apples is something that they could not even conceive, because 0 means empty. No, 0 apple can be also 0 cabbages, 0 whatever. Is nothing. Nothing is nothing. So cannot be quantized in units. And even the unit is not a number. It's just the object. And then you count how many of these objects you have. So U and V are some, we would say, numbers. They say some grandezze, some extensions of something. And you would like to find 2 numbers, x and y, so 2 extensions of the same something, such that the ratio of u to x is equal to the ratio of y and equal to the ratio of y to v. So you have to find these numbers x and y. Obviously, how do you do? Well, it is very simple. You see, this is equivalent to cubic roots, because now what you do, if you multiply all these numbers among themselves, on one side, you find that u over x times x over y times y over v. Now you make the cancellation. This is u over v. But on the other hand, since all these 3 numbers, 3 ratios are equal, you can say that u cube over x cube is equal to uv. So as you see, x cube, now if you solve the cubic equation, you see that x cube is equal to u cube multiplied by v over u. So you see that u squared over v is equal to x cube. Now, this is how we argue nowadays. But the point was the following, that it was the Hippocrates of Kiel that reduced the problem of the duplication of the cube to the problem of finding the numbers x and y. Because now if you have the number x and y, you can easily find the number u that satisfies that solves the problem, namely u cube is equal to 1 over v multiplied by x cube. Okay, so if v is, for instance, 1 over 2, then you have solved the duplication of the cube, because you have x was the original psi of the cube. The cube that has volume twice as much is obtained with number u provided the number v was 1/2, which was rational, so accepted by the Greek. But they went through the idea of finding the intermediate numbers x and y, solving these proportions, because they were thinking in terms of proportions. And it was thinking in terms of proportions that XXth found a way of constructing this proportion by going through a geometrical construction that involved a torus, a cylinder, and a cone. But since it's 6 o'clock, I think we will see the in the next lecture. I hope you have been following. In this lectures, the important thing is to understand how trivial things are non-trivial. Okay, in order to understand the development of the human logic and abstract thinking that was necessary to find trivial things that for them were absolutely non-trivial. Do you have questions on my lectures of today?
No.
Era tutto abbastanza chiaro, sì?
Yes.
Okay. So we meet next Monday, right?
Yes. See you next Monday.
See you on next Monday, and nice evening. Eh?
Bye.
Okay.
See you.
See you
Good
soon.
weekend.
Buona serata anche a lei, grazie.
Grazie anche a lei, grazie a tutti per avermi ascoltato. Arrivederci.